Imagine you have a plant that doubles in size every day. On day 1, it's just 1 unit tall. On day 2, it's 2 units. On day 3, it's 4 units. Writing 2 times 2 times 2 every time gets messy. So mathematicians invented a shortcut, the exponent. The exponent is a tiny number written up high that tells you how many times to multiply a base number by itself. The base is the number you're multiplying, like the 2 in our plant example. And the whole thing, base and exponent together, is called a power. So 2 to the third power means 2 multiplied by itself 3 times, 2 times 2 times 2, which equals 8. It's just compact notation for repeated multiplication. Why do we even bother with exponents? Because they let us write huge numbers in a tiny space. Think about our doubling plant again. After 10 days, you'd have to write 2 times 2 times 2 10 times. With an exponent, you just write 2 to the 10th power. That's 10 2's multiplied, which is 1024. Exponents also reveal a hidden pattern. They show how things grow by repeated multiplication. This isn't just about plants, it's how money grows with compound interest, how populations explode, and how computer memory doubles. In calculus, you'll see exponents everywhere, in polynomial functions, in the number e, and in rates of change. Mastering them now is like learning the alphabet before you read a book. Let's build this from the ground up. The exponent tells you the number of copies of the base to multiply. So 2 to the third power means 3 copies of 2, 2 times 2 times 2. But here's a trap, 2 to the third is not the same as 3 to the second. 2 cubed is 2 times 2 times 2, which is 8. 3 squared is 3 times 3, which is 9. The base and exponent are not interchangeable, they mean completely different things. Now, what about an exponent of 1? 2 to the first power means just 1 copy of 2, so it's just 2. Makes sense, multiplying by itself 0 extra times leaves the number alone. And the strangest one, 2 to the 0 power. Why is that one? Look at the pattern, 2 cubed is 8, 2 squared is 4, 2 to the first is 2. Each step down divides by 2. Let's solve a concrete problem. A tall tree casts a shadow that is 16 meters long at noon. Each hour, as the sun moves, the shadow's length halves, it multiplies by 1/2. What is the shadow length after 3 hours? We start with 16 meters. After 1 hour, it's 16 times 1/2, which is 8 meters. After 2 hours, it's 8 times 1/2, which is 4 meters. After 3 hours, it's 4 times 1/2, which is 2 meters. We can write this compactly with an exponent, 16 times 1/2 to the third power. 1/2 cubed means 1/2 times 1/2 times 1/2, which is 1/8. 16 times 1/8 equals 2. So the shadow is 2 meters long. Notice the base here is a fraction, but the exponent rule works exactly the same. The exponent just counts how many times we multiply by that fraction. This same method solves any repeated halving, doubling, or scaling problem. Just identify the starting value, the multiplier, and the number of steps. You already know that an exponent tells you how many times to multiply a base by itself. So 2 to the power 3 means 2 times 2 times 2, which is 8. But what if you multiply that by 2 to the power 2? You could write out all the 2's and count them, but that gets messy with big numbers. The exponent laws are just shortcuts that let you combine powers without writing out every single multiplication. They aren't new magic rules, they're just the natural pattern that falls out of the definition of repeated multiplication. Today we'll look at the 3 most important ones: multiplying powers, dividing powers, and taking a power to another power. Imagine you're working with a really huge number, like 10 to the power 20. Writing that out as a 1 with 20 zeros is tedious and easy to mess up. Now imagine you need to multiply that by 10 to the power 15. The exponent laws let you do it in one step. Just add the exponents to get 10 to the power 35. This isn't just about saving ink. It's about seeing the structure of a problem. When you see an expression like x to the power a times x to the power b, you don't need to panic about what x, a, and b are. You know it simplifies to x to the power a plus b. This pattern recognition is the bedrock of algebra, and later, it's how you'll handle everything from polynomial multiplication to the chain rule in calculus. It turns a mountain of multiplication into a simple addition problem. Let's derive these rules from scratch. For the first rule, take 2 to the power 3 times 2 to the power 2. 2 cubed is 2 times 2 times 2, and 2 squared is 2 times 2. If we multiply them, we just have a chain of 5 2's multiplied together. That's 2 to the power 5. So we added the exponents, 3 plus 2 equals 5. The second rule is the flip side. What about 2 to the power 5 divided by 2 to the power 2? That's a fraction with 5 2's on top and 2 on the bottom. 2 of the top 2's cancel with the bottom ones, leaving 3 2's, or 2 cubed. So we subtracted the exponents, 5 minus 2 equals 3. The third rule is about a power raised to another power, like 2 cubed, all squared. That means the whole block 2 cubed is multiplied by itself. So we have 2 to the power 3 times 2 to the power 3. Let's use these rules on a real problem. Imagine a small cube with a side length of 2 centimeters. Its volume is 2 cubed, which is 8 cubic centimeters. Now, a scientist grows the cube in 2 steps. First, she doubles the side length, so the new side is 2 times 2, or 4 centimeters. Then she triples that result, so the final side is 3 times 4, or 12 centimeters. We want to know how many times bigger the final volume is compared to the original. The final volume is 12 cubed. But we can write 12 as the original side, 2, multiplied by 2 and then by 3. So the volume is 2 times 2 times 3, all cubed. Using the power of a power rule in reverse, a product raised to a power is each factor raised to that power. So we have 2 cubed, times 2 cubed, times 3 cubed. That's 8 times 27, which is 1728. The original volume was 8. We already know that a positive whole number exponent, like 2 to the 3, means multiply 3 copies of 2 together. But what if the exponent is negative, like 2 to the minus 1? Or a fraction, like 2 to the half? These aren't repeated multiplication anymore. You can't multiply half a copy of something. So we need to extend the definition. A negative exponent means repeated division instead of multiplication, so 2 to the minus 1 is 1 over 2. A fractional exponent like 1/2 means a root, the number that, multiplied by itself, gives the base. So 2 to the half is the square root of 2. These new kinds of exponents fill in all the gaps between the whole number powers, letting us define 2 to the x for any real number x. Why bother with these strange exponents? Because we want the exponent laws to work for all numbers, not just positive whole ones. Take the division law, 2 cubed divided by 2 squared is 2 to the 1, which is 2. But what about 2 squared divided by 2 cubed? Using the law, we get 2 to the minus 1. But actually doing the division gives for over 8, which is 1/2. So to keep the law consistent, 2 to the minus 1 must equal 1/2. That's the purpose. Negative exponents are just reciprocals. Similarly, the power of a power law forces fractional exponents to be roots. If we want 2 to the half, squared, to equal 2 to the 1, then 2 to the half must be the square root of 2. This lets us define a continuous curve y equals 2 to the x, with no gaps, which is essential for calculus. Let's derive these from first principles using the exponent laws we already trust. Start with the division law, 2 to the a divided by 2 to the b equals 2 to the a minus b. If a is smaller than b, the exponent becomes negative. For example, 2 to the 2 over 2 to the 3. By the law, that's 2 to the 2 minus 3, or 2 to the minus 1. But if we just calculate the numbers, it's 4 over 8, which simplifies to 1/2. So 2 to the minus 1 must equal 1/2. In general, 2 to the minus n equals 1 over 2 to the n. Now for fractions, use the power of a power law. We want 2 to the 1/2 squared to equal 2 to the 1/2 times 2, which is 2 to the 1, or just 2. So 2 to the 1/2 is the number that squares to 2, that's the square root of 2. Let's solve a concrete problem. What is 8 to the 2/3? This looks intimidating, but we can break it down. The denominator 3 tells us to take a root, specifically, the cube root, because we need a number that, multiplied by itself 3 times, gives the base. The cube root of 8 is 2, since 2 times 2 times 2 is 8. The numerator 2 tells us to then raise that result to the power of 2. So we square the 2, getting 4. Therefore, 8 to the 2/3 equals 4. We can check this, 4 to the 3/2? No, let's verify by working backwards. 4 is 2 squared, and the cube root of 8 is 2, so 8 to the 2/3 is 2 squared, which is 4. This method works for any fractional exponent. Denominator gives the root, numerator gives the power. Imagine you have a secret code machine. You put in a number, it raises 2 to that power, and out pops the answer. You know the answer is 8, but you forgot what power you put in. You need a rewind button. That rewind button is a logarithm. A logarithm asks the question backwards, given a base, like 2, and a result, like 8, what power did we raise it to? We write this as log base 2 of 8 equals 3. The little subscript 2 is the base, the number 8 inside is called the argument, and the answer 3 is the power, or exponent. So a logarithm is just an exponent finder. It's the reverse question of exponentiation. We know exponents are about repeated multiplication, a fast-forward button for growth. But what if you know the final amount and the growth rate, and you need to find the time? That's exactly the problem logarithms solve. Think of a bank account doubling every year. You want to know how many years it takes to grow from $1 to $8. You could guess, 1 to 2 is 1 year, to 4 is 2 years, to 8 is 3 years. But what if the numbers aren't neat? A logarithm is the mathematical tool that asks a what power, for any number, not just easy ones. It's the inverse operation, like subtraction is to addition. It unwinds the exponential process, letting you travel backwards from the result to the exponent that made it. Let's build the logarithm from the exponent rules you already know. You know that 2 raised to the power of 3 is 8. The logarithm simply reads this statement backwards. The base of the logarithm is the same base from the exponent. The argument is the result of the exponentiation. And the answer, the logarithm itself, is the exponent. So log base 2 of 8 equals 3 is just a compact way of saying that the power I need to raise 2 to, in order to get 8, is 3. The word a log is short for logarithm, which comes from Greek words meaning ratio number. It's a number that expresses a ratio, or relationship. Every logarithmic equation is just an exponential equation in disguise. If you see log base b of a equals c, you can instantly rewrite it as b to the c equals a. This back and forth is your superpower. Let's use a logarithm to solve a real problem. A single bacterium doubles every hour. How many hours until there are 16 bacteria? We start with 1. After each hour, we multiply by 2. So the number of bacteria is 2 raised to the power of the number of hours. We want to find the exponent when the result is 16. We set up our logarithm, log base 2 of 16. This asks 2 to what power gives me 16. We know 2 times 2 is 4, times 2 is 8, times 2 is 16. That's for multiplications by 2. So 2 to the power of 4 is 16. Therefore, log base 2 of 16 equals 4. It takes 4 hours. The logarithm found the hidden exponent for us. This same method works for any growth problem where you know the factor and the final amount, but need the time. You already know that an exponential function like 2 to the x grows faster and faster as x increases. But there is one very special number, about 2.718, that we call e. If you use e as the base, the function e to the x has a magical property. At every single point, the slope of the curve is exactly equal to the value of the function itself. So when the function is at height 3, its slope is 3, when it's at height 1, its slope is 1. The natural logarithm, written ln of x, is simply the logarithm with this same special base e. It's the inverse of e to the x, just like log base 10 is the inverse of 10 to the x. Why do we care about this strange number e? Because nature itself seems to love it. Many things that grow or shrink continuously, like a population of bacteria, the cooling of a hot cup of tea, or the charge on a capacitor, follow a pattern where the rate of change at any moment depends on how much is there right now. More bacteria means faster growth, a hotter cup cools faster. The function e to the x captures this perfectly, its rate of change is exactly itself. This makes calculus incredibly clean. Instead of messy constants, the derivative of e to the x is simply e to the x again. And its inverse, ln of x, has a derivative of 1 over x, which is beautifully simple. This pair unlocks a huge chunk of physics and engineering. So where does e actually come from? Imagine you have 1 rupee in a bank that pays 100% interest per year. If it compounds once a year, you get 2 rupees. If it compounds twice a year, you get 1 plus 1/2 squared, which is 2.25. If it compounds monthly, you get about 2.61. As you compound more and more often, every second, every millisecond, the total doesn't explode to infinity, it creeps up to a limit of about 2.718. That limit is e. The natural log, ln of x, can be thought of as the area under the curve 1 over t from 1 to x. And because e to the x and ln of x are inverses, their graphs are mirror images across the line y equals x. Pick a point on the e to the x curve, swap its coordinates, and you land on the ln curve. Let's solve a real problem. A bacteria colony starts with 1,000 cells and grows continuously at a rate of 20% per hour. The population after t hours is given by 1,000 times e to the 0.2 t. We want to know when the population triples to 3,000 cells. Set up the equation 1,000 e to the 0.2 t equals 3,000. Divide both sides by 1,000 to get e to the 0.2 t equals 3. To undo the exponential, we take the natural log of both sides. The ln of e to the something is just that something, so we get 0.2 t equals ln of 3. ln of 3 is about 1.099. Divide by 0.2 to get t equals about 5.49 hours. So in about 5.5 hours, the colony triples. This same method, using ln to solve for an exponent, works for any exponential equation in science and finance. We've already seen that a logarithm is the inverse of an exponent. It asks, what power did we raise the base to? Now we're going to see why that's so useful in the real world. A logarithmic scale takes numbers that span an enormous range, like the energy of earthquakes or the growth of money over decades, and squashes them down into small, manageable numbers. Imagine a ruler that stretches and scrunches so that each equal step multiplies the thing you're measuring by a fixed amount. That's exactly what the Richter scale does. A magnitude 6 quake shakes the ground 10 times more than a magnitude 5. And in finance, the rule of 72 uses the natural log of 2 to tell you how many years it takes for your money to double, just by dividing 72 by the interest rate. Both are logarithms hiding in plain sight. Why do we even need a logarithmic scale? Because nature throws numbers at us that are absurdly far apart. An earthquake you can barely feel, and one that flattens a city release energies that differ by factors of millions or even billions. If we plotted that on a normal graph, the small quakes would be invisible, squashed against zero. The Richter scale solves this by using a base 10 logarithm. Each whole number step multiplies the ground shaking by 10. So a gentle magnitude 3 and a catastrophic magnitude 8 are only 5 steps apart on the scale, but the shaking is 100,000 times stronger. It compresses an unreadable range into a simple 1 to 9 scale that anyone can understand at a glance. Let's open the hood and see where these numbers come from. The Richter scale is defined as the base 10 logarithm of the maximum ground shaking amplitude, measured in microns, recorded by a seismograph. So if one quake shakes 10 times more, its log increases by 1, and its magnitude goes up by 1. But the energy released is trickier. It scales with the amplitude raised to the power of 3/2. That means a 10 times shake actually releases about 32 times more energy, because 10 to the 3/2 is 10 times the square root of 10, which is roughly 32. Now for money, we start with the compound interest formula. Amount equals principal times 1 plus rate to the power of time. Set the amount to double the principal, take the natural log of both sides, and you get time equals natural log of 2 divided by natural log of 1 plus rate. Let's put this to work with two quick everyday problems. First, earthquakes. A news report says a magnitude 7 quake just hit, and you remember a magnitude 5 last year. How much more energy did this one release? The difference in magnitude is 2. Since energy scales as 10 to the power of 1.5 times the magnitude difference, we compute 10 to the power of 2 times 1.5, which is 10 cubed, or 1,000. So the magnitude 7 quake released 1,000 times more energy than the magnitude 5. That's why a small number change on the Richter scale means a huge difference in destructive power. Second, your bank offers an 8% annual interest rate. How long until your savings double? Using the rule of 72, just divide 72 by 8, giving 9 years. Let's zoom out and see the whole map. We started with exponents, a shorthand for multiplying a number by itself over and over. That's growth by repeated doubling or tripling. Then we met logarithms, which ask the reverse question: what power did you raise the base to get this result? They are perfect inverses, like a lock and key. One builds a number up, the other takes it apart to find the hidden power. And when we use the special number e as the base, we get two beautifully smooth, continuous functions, e to the x, and its inverse, the natural log of x. They connect repeated multiplication to the idea of a continuous curve, which is exactly what calculus needs. Why do we care so much about these two functions? Because the real world doesn't grow in sudden jumps, it grows continuously. A population doesn't double once a year, it's growing every second. Money with compound interest grows while you sleep. Radioactive atoms decay smoothly. Exponents and logs are the language of that smooth, ongoing change. They also have a magical property: they turn multiplication into addition, which makes hard problems easy. And here's the big preview for calculus: the slope of e to the x is itself, and the area under the curve 1 over x is the natural log. These functions are the bridge from simple algebra to the powerful ideas of derivatives and integrals that we're about to explore. Let's build this from what we already know. You've seen that an exponent like 2 to the 5th means 2 times itself 5 times. But what if the power isn't a whole number? We learned that fractional powers are roots, and negative powers are reciprocals. Now, imagine filling in all the gaps, every possible power, not just fractions. That gives us a continuous curve. When we choose the base e, about 2.718, we get the function e to the x. It's special because its instantaneous rate of change at any point is exactly its value at that point. The natural log, written ln of x, is its perfect inverse. It asks, to what power must I raise e to get x? So ln of e to the x is just x, and e to the ln of x is x. They perfectly undo each other, like a round-trip ticket. Let's solve a concrete problem. A colony of 100 bacteria grows continuously at a rate of 20% per hour. The population after t hours is 100 times e to the power of 0.2 t. We want to find the doubling time, how long until there are 200 bacteria. So we set up the equation, 200 equals 100 e to the 0.2 t, divide both sides by 100 to get 2 equals e to the 0.2 t. Now we need to unlock that exponent. We take the natural log of both sides. The natural log of e to the 0.2 t is just 0.2 t, because ln and e undo each other. So we have ln of 2 equals 0.2 t. Ln of 2 is about 0.693. Divide by 0.2, and we get t is about 3.47 hours. That's the doubling time.